So I'll turn it over to questions and answers.
Yeah. Could you go to a microphone so everybody can hear you?
I was looking for the way the MSR will produce electricity, and it never mentioned that at all.
The what?
How the MSR is going to produce electricity.
Okay, I'm deliberately saying we don't want to produce electricity to start with. We want to take biomass. Instead of boiling water, we want to boil biomass and make artificial coal, artificial gasoline, artificial natural gas. You can make electricity by the same way that we do it now, which is to boil water into steam or use a gas turbine. That is not any different. It doesn't have a huge advantage. There are many ways to do electricity. We would want to do it to make things carbon negative. So let me just show this thing. It's very simple. We have here not molten fluoride salts, but molten acetate salts, which we keep at 300 degrees. We've done laboratory experiments. We know if you take any biomass and you keep it there for 10 minutes or longer, it will char. It's like bad cooking, okay? It just burns. Except you do it without air. It's below the salt level, so there's no air. It doesn't actually burn. So it all turns into char. So if you take stems or leaves, it becomes charcoal. So on one side you come in. And the way to keep the air out is just to do underwater swimming, because we also need to wash the salt off. So you load the biomass onto here. Out here you have air. We remove the top and the front so you can't see it. You let it swim under a partition. Now there's no more air. It's only got whatever biomass puts out, which is water vapor, other things like methanol, which we can use to transesterifize vegetable oil into biodiesel. We have acetic acid, which can be turned into acetone or convert potassium and sodium salts into the salts that we need to run this reactor. It has furfural, which is a biodiesel additive, and you also have volatile organic compounds that you drive off, that's syngas, and that replaces natural gas. There's zero waste in this process. We're building a unit like this, hope to complete it within 2 years, and be taking care of the garbage, and this highly invasive tree that was introduced to the island, which the government now wants to get rid of. Okay? We'll process 100 tons a day. This is exactly the amount that Palo Alto wants to solve the problem. We've talked to the city of Palo Alto. This scale of this thing is given by two figures. I think you know the Darth Vader. He's about 2 meters tall, so you can tell how tall. This is not 10 acres. This is a tenth of an acre compared to biodigestion. And then this is R2-D2. Of course, in these kind of situations, the big guy gets to be supervisor. Little guy does all the work. Since he does all the work, I suspect R2-D2 is a woman. That's how we want to do it. So you use this stuff, which is easy to use. You either use this, you can burn it if you want. We suggest it should just be buried to improve the soil. You can burn this stuff, you can burn this stuff. No, but it was taken out of the air the previous year by biomass. It's carbon neutral. When you bury the coal, it becomes carbon negative. If you ever want to go to carbon zero, you have to have something that's negative. And the reason is because everything else we might electrify, you cannot electrify an airplane. I wouldn't want to fly in an airplane that ran on batteries. Okay? I don't think anybody would. Okay? So you always have to make that piece. And that's not trivial amount. This is carbon neutral, and if you bury the charcoal, it becomes carbon negative. And in a safe way. Coal does not rot, right? Charcoal, you have a bag of charcoal in your garage. You don't have to worry about it going bad, right? You can leave it next season. You can leave it for 1,000 years. It does not rot. But biomass, if you just let it stay on the ground, it will rot. It will give you not only carbon dioxide, it will give you methane. right? That's what Palo Alto went through all this argument. You put it in a landfill to make compost. It's actually worse than if you had burned it. Here, we don't burn it. We heat it up, driving out the stuff that would make it rot, and using that as fuel. The other stuff is buried. You can bury this anywhere, by the way. So suppose you want to burn a gallon of gas and put up that carbon dioxide. You don't have to take care of it here. You can say, if you burn a gallon of gas to make it carbon neutral, somebody in Southeast Asia, let's say the Philippines, has to make an equivalent amount of coal or biochar that they bury. It would improve their soil. Everybody would be better off.
Is this a fast reactor?
No, this is a thermal reactor.
Oh, it's going to be a thermal reactor. Oh,
Yes.
okay.
Otherwise, we don't have enough plutonium. Okay, I can show you a slide. U.S. has enough plutonium. We have enough spent fuel such that we can do this conversion, supply all the energy needs before the end of before the middle of the century.
I'm still you got me up to the point where we generated all the the neutrons, we generated heat, and could we also use it to generate electricity directly
Yes.
with the board?
But you would not be any better off than light water reactors, except you make more nuclear fuel. So yes, this could be used to generate electricity.
But and the advantage is less of the the bad byproducts as opposed to a light
Yeah,
water reactor.
you don't
and
have
and
the
a
bad
safety aspect.
byproducts. If you you have the blanket salt will become radioactive. It will become because it sees neutrons. But if you transfer it to another salt, you can use that salt to heat water or gas and generate electricity by
And
the
also
conventional way.
Curious about the scale. The economy is a scale.
Oh, okay, good.
In other words, how big would this be? Let's say municipal garbage for the Bay Area. Did you need that in order to generate what you need to make your money?
Okay,
What size are we talking about?
okay. So most people don't realize is that a nuclear reactor can be run at any level you like. The upper limit is set by whether you can remove the heat. Okay, so here is a graphite heat exchanger. It's about 1 foot cubed, and it can transfer, if we had nuclear power, it's too small to run a chain reaction, but if we did, it can transfer 140 megawatts of heat, which is enough to power all the energy needs of 30 homes. So that's how powerful this stuff is.
30 homes.
Yes, 30 homes. 140 kilowatts, excuse me, 140 kilowatts, okay? If you scale it up, you just go as a wide. So to power something like the Bay Area, right, you would need maybe 4 meters.
So in South San Francisco, there's a garbage plant, and they process garbage. You could put one there, process
so
that
now
garbage,
we're
and
talking
generate
about
electricity and stuff?
Yeah, so this thing is about, for Palo Alto, is about a 1.4 megawatt thing. Yeah, okay. So this thing is about 1.4 megawatts.
And the average nuclear power plant is?
Oh, gigawatts.
Yeah.
We don't want to build them that big.
So
One
we're
of the
talking.
problem is that people build these huge things, which then it's very hard to take care of the
So we're talking about a lot of small area. Okay, that's
100
what I'm trying to
megawatts.
understand the concept.
100
Okay.
megawatts, yeah. That's sort of the ideal size.
Question to this side?
Yeah.
I have two brief questions. First, can you compare and contrast the molten salt reactor to another advanced reactor type like the lead fast breeder reactor? And
Yeah.
also, if you could speak a little bit to the removal of the fission products and the poisons. I think you mentioned the xenon 135.
Right.
As that builds up, it has an effect on your efficiency.
Xenon 135 is very easy to remove in this reactor because it's a gas. So it will bubble out of the pump bowl, okay? The thing that you don't want is that it goes into the reactor before it gets to the pump bowl. That's why you want to seal the reactor. The lead fast reactor or the bismuth fast reactor is very similar to the sodium fast reactor. It's still solid fuel elements, still fast neutrons, okay? It's just that the trick to finding things so it doesn't absorb neutrons, is to find elements that only have one stable isotope. Okay? Lead has quite a few, but it turns out it's not so, none of them are very absorptive. Bismuth is one isotope, sodium is one isotope. So they're all the same. They all have, they're better than sodium in the sense that, they don't catch on fire so easily. But there are also less of them that have been built, fewer. This reactor has been built, okay, but it was never used. Nobody asked me why. You asked me privately, so I will tell you my guess why. See, this reactor was built at Oak Ridge when Alvin Weinberg was the director. In 1972, Alvin Weinberg made the statement that light water reactors are not safe enough. Now, he holds some of the most important patents on the light water reactors. So he knew what he was talking about. And he had in mind the reactor they built, the molten salt reactor that they built at Oak Ridge. He was immediately hauled to Congress because I told you, it was national policy to sell light water reactors to the rest of the world. You have the director of a national lab saying that they're not safe enough. So he was told, if you think safety should be a major concern of nuclear power generation, maybe you should not be the director of Oak Ridge. He was fired. The next year, the project was canceled. And 6 years later, we had 3 Mile Island. Okay? So he was prophetic in this. Now, the PI of the project has a somewhat different thing. You can find all this on the internet. He said it failed because there were too many entrenched interests. So, that's a politic way of saying something. So you have to read between the lines. What was he trying to say? Here's my reading. Where are the entrenched interests? Number one, the military. The military was against this reactor because it doesn't produce plutonium. It destroys plutonium. At that time, we wanted more and more plutonium. So you don't have the military with you. You don't have industry with you. Because at that point, remember, I said, height of nuclear activism, people were not selling reactors, at least not much, in this country. So how were they making money? They made money the Gillette way, right? They don't make any on the razor. You want razor blades. Well, boy, they're expensive. Or, Hewlett-Packard doesn't make money on printers, but you want ink. Similar in the nuclear reactor business. They were making money because fuel requires fabrication. Liquid fuel does not require fabrication. Do you have enough for a chain reaction? Oh, not enough. Add some more. Enough? No, add some more. Half competent chemists can do that. You don't need a huge team. So you don't have industry behind you, right? Plus, everybody else is working on the sodium fast breeder reactor or other things. And, they review your proposals. Oh, it's not as good as us. Maybe there was a question at some point which one was better. But I can tell you that in the Manhattan Project, there was also this question. And they had a rule, the United States at that point. We had this rule. If we came to a decision point, we couldn't decide which path was better, we would take both of them. That's why we got 2 bombs. One was a uranium-235 bomb. The other was a plutonium-239 bomb. Somehow, between then and the period I was talking about, we lost that vision. If you don't know, and it's really important, you should follow all leads. By the same token, I don't know this reactor will work. I don't think we should stop work on the sodium fast breeder reactor. I don't think we should stop work on solar photovoltaics. We should do all of them at a research and development level. Okay? Right. But I know the government is not going to support this reactor. So one of the reasons we're doing this waste project management is because we hope enough people can see that without controversy. We can get funded to do that and earn enough money so we can build this reactor in the private sector. That's really my goal. I'm 68. I'm probably not going to see this reactor. Okay? But I want to get us far enough along so I can feel safe about, your children, your grandchildren. We're doing this for them.
Along that last line, the light water reactors, which are used universally, essentially came out of the naval project, and the Westinghouse and General Electric were the prime movers. I was wondering whether there's any prom firm like those two or others who are pushing and making aware to the utilities of the molten salt reactor and making them or offering them as commercial units.
So, I've talked obviously to the utility company in Taiwan. I can tell you their
That's
reaction.
it.
You build it, we'll use it. But we're not going to give you any money to build it.
Okay. One more question then.
But I would
excuse
like to
me.
follow up on your original question, which is who funded this reactor to begin with? It was the Air Force. They were jealous of the Navy having nuclear-powered submarines, so they wanted nuclear-powered airplanes. Now, they had a good reason for wanting it, because at that time, we were in the Cold War with the Soviet Union. We were afraid they were going to give a first attack, right? Take out all our bombers. So we wanted the bombers. We kept a fleet of bombers flying all the time. Well, if you had a nuclear-powered airplane, it could fly for months, just like, okay, and without coming down. But of course, if you really think about it, that's really a bad idea, right? The only good idea about it is that the enemy won't shoot it down, not over when it's flying over them. So eventually, the first reactor was canceled, and the second one was built. Okay. So often people say, well, these reactors can't be load following. That's nonsense. Think of an airplane. Goes in a dive. You need to come out of the dive. You better have the power when you need it. And this reactor was built so it could do that. You just pump harder. It'll give you whatever power you want.
Yeah. General Electric had a project for aircraft nuclear propulsion, and they did have a contract out in Cincinnati to construct a nuclear-powered plane. I don't know whatever happened to it, but I just remember that was the case. But the other matter was just my understanding of the molten salt process. In a light water reactor, we have fuel rods with pellets in them enclosed within the liquid. Would we have pellets of
Just a
thorium, or we could use thorium and put them in.
So you have
in
two
rods.
channels in our design. You have two channels, one of which holds the blanket salt. It's also out here. They absorb neutrons,
And what form is the blanket?
It's in the form of a
it's the
liquid salt.
thorium.
but it has thorium.
Thorium oxide.
Yeah,
Not in
thorium, no,
pellets,
it's
but
fluoride.
just-
Thorium fluoride. And in the fuel, you have uranium fluoride,
Mhm.
uranium-233.
Yeah.
And you don't need control rods. You can have control rods. if
What
you-
is the form of the thorium that's loaded into the blanket?
It's in a salt. We like
It's-
sodium
it's-
fluoride,
It's a
beryllium
powder?
fluoride.
It's a powder?
Well, it becomes a liquid. It just becomes a
Liquid.
solution.
Thank you.
What are the temperatures we're talking about?
So initially, you would run them probably at 750 or so, because that's all Hastelloy N is qualified to do, centigrade. And eventually, you would like to run them above 900 C. At 900 C, the materials become difficult. Very few metals have been qualified, especially for nuclear work. None, in fact, at such temperatures. So you have to find new alloys. But that's a magic number, because at that point, you can thermally, chemically dissociate water. If we could ever make water a fuel, right, that would be tremendous. Hydrogen and oxygen. Yeah. Right now, you can generate hydrogen and oxygen by electrolysis, but the electricity is worth more than the hydrogen and oxygen, so what's the point?
With those temperatures, you have a better Carnot cycle. for
Yes,
those, And you can use that for generating heat then.
yes. You're generating electricity, yeah.
We have reached the end of our time here. I want to again thank SRI for opening the room to us. Professor Hsu, thank you very much for making the trip and bringing your ideas and your research to us and opening the discussion on this important topic. We are much obliged.